We are starting chapter 2 today, and chapter 2 is specifically on linear relations and functions, but this first section just reviews in general what a relation is and then what a function is. So today you want to be able to say that you can analyze relations and functions, and what that means is find the domain and range of a relation and a function, determine if a relation is a function, and then specifically with functions, determine if they're one-to-one functions or onto functions. So we'll talk about what those mean, because I believe these two terms are introduced in Algebra 2. They wouldn't have been introduced in Algebra 1. And then the second part of it is looking specifically at relations written as equations and determining if those are functions as well, and then also how to evaluate functions with function notation. So there's kind of a lot of review going on, but mixed in there is some terminology that is maybe going to be new to you. So I have at the top a reminder of what a relation is. So it is a set of ordered pairs in the form XY. Specifically, that's kind of the formal definition. This is how I define a relation. It's a relationship between X and Y. So ordered pairs really show how X values and Y values are related to each other. More specifically, I guess if you think of an equation, that really shows how X and Y would be related to each other. And the solutions to that would be ordered pairs. So by definition, a set of ordered pairs, but it's a relationship between X and Y. And then a function is a specific type of relation. So it's a relation in which each element of the domain, which is the set of all of the X values, is paired with exactly one element in the range, which is the set of all of the Y values. So there's kind of three definitions there, I guess, that are being reviewed. So first of all, the domain is the set of all of the X values in a relation. The range is the set of all of the Y values. And then a function specifically is if each domain value, each X value, is paired with exactly one Y value. So that means you don't have multiple, or you don't have one X value paired with multiple Y values. So we are going to be looking at a lot of examples determining if they are functions. So we'll be talking more about that definition. And then before we get into examples, if you know that you have a function, so one-to-one and onto are specific to functions, so not relations, but functions in general. A one-to-one function means that each element of the domain, so the X values, each element of the domain pairs to exactly one unique element of the range. So another way of saying that is each X value is paired with a different Y value, or no X values are paired with the same Y values. So I'm going to include that if you want to write that down. That might be an easier way to remember it, that no X values are paired with the same Y value. And then it does give an example there. This is called a mapping, where you specifically see domain, range, and then it's showing you how one element of the domain, what it's paired with in the range. But in this mapping, this would be an example of a one-to-one function. So every element in the domain is paired with a different element in the range. So you don't see any of these values, 1, 2, or 3, going to the same range value. So if you were to look at the next one, before I even talk about what onto is, this is not one-to-one, because if you notice, 3 and 4 are both going to C. They're both paired with C. So while this is going to be an example of onto, it is not a one-to-one function. And then if we look at what onto means, this says each element of the range corresponds to an element of the domain. So what that means is if you are given a set of values that are in the range, all of those range values are going to be used in the function. So another way to think of that is you don't have any unused values. So I'll say here no unused y values. And that example in that box is a function that is onto. And the reason why is if you look at the range, you have D, B, and C. And these are all paired with at least one value in the domain. Versus if we look back at that first box, notice here in this range, D, B, C, and A, C is not paired with anything, meaning it's not onto. So basically, here you have an example of a function that is one-to-one, but if you want to make a note, this one is not onto because of that leftover range value that isn't paired with anything. And then in the second box, this is an onto function, but it's not one-to-one. And that's because the elements 3 and 4 are both paired with the same range value C. So that's why it's not one-to-one. And then I'm not going to read through what it means to be both because I find it easier to just look at one-to-one and then onto separately. And if you can say, yes, it's one-to-one, yes, it's onto, then it's both. So just look to see, are any of the x values paired with the same y values? Are any y values not used? Answer those questions versus trying to understand what this is saying. It's saying the same thing. I just know that how they word it, it can get kind of confusing. So that box is just putting together what it would look like if it's both. So under example 1, there's actually 4 examples. Relations can be represented as just a set of ordered pairs, as a table. It does continue on to the next page. So there's a graph example and there is a mapping example. So I included different representations of relations and then obviously answering the questions, they're all a little bit different. So we're going to state the domain and range of each relation and then determine is it a function, and then if it is a function, determine if it's one-to-one, onto, both, or neither. And basically you're going to see what I have. You're just saying is it one-to-one, yes or no, is it onto, yes or no. So you don't have to then say it's both or it's neither. You're just saying yes or no for each one. So if we look at example A, the domain, I'm going to kind of talk through these definitions again as we go through the first example. The domain is the set of all of the x values in the ordered pairs. So we know x is the first value in an ordered pair. And so my x values, I have -6, -5, -3, -1, +6. So they're all different. So when you're writing the domain, I'd like you to write it inside of the braces because it is a set of numbers and those braces define what a set is. So inside the braces, I'm just listing the x values. When we go through these examples up here, I am going to write them in numerical order. However, say on a quiz or test when I'm grading your work, as long as you have all of the correct values, if they're not in numerical order, I'm not going to mark it wrong. So I'm just making sure you have all the right values. It's best or it's more appropriate for them to be in numerical order, but if they're not, it's not incorrect. And then the range, this is the set of the y values in the ordered pairs, so all of the second values. So we have -1, -9, -7, +7, and then -9 again. So if you see a value that repeats, you only need to list it once. And I'm actually going to write the -9 first since it's the smallest, and then -7, and then -1, and then +7. But again, if your order is different, as long as you have all 4 values in there, it's fine. So then there's the question, is this a function? So again, at the top, I'm just going to move this for a minute. At the top, a function means that every x value is paired with exactly one y value, meaning you aren't going to see one x value paired with 2 or more different y values. So what you're looking for to determine if it's a function, you're going to look for repeated x values. Because if you see that two different ordered pairs have the same x value, it means that one x value is paired with two different y values and it's not a function. So since every ordered pair we have has a different x value, this is a function. So yes, it is a function. Every ordered pair has a different y value, or different x value, I'm sorry. And then for a function to be one-to-one, so if you're saying yes, it's a function, you have to answer the next two. These are specific to functions. So then looking to see is it one-to-one at our definition above, this means that no x values are paired with the same y value. So for one-to-one, you're going to look for repeated y values. So if two or more ordered pairs have the same y value, it is not one-to-one. But if all of your y values are different, then it is one-to-one. So because we had two different ordered pairs with the y value -9, that means two x values are paired with the same y value. So no, this is not one-to-one. And then for a function to be onto, this one is just a little bit strange. So the best way I can think to explain it from how we saw it above, I'm going to look back at this first box again because this was an example where it's not onto. So for you to say no, it's not onto, that means you would be given the range ahead of time and you would be told these are the values in the range. And then you would see in your example that one or more of those values are not used. So that's not the case here. We weren't given a list of values in the range, and then we saw that one or more of them isn't being used. So yes, this is onto. All of the values that are in our range were used from the ordered pairs. Basically, the only time this is going to be no is if you are given a mapping, and you can actually see this range value isn't being used. That's really the only time that would be no, unless, of course, if it's not a function, then it's not either one-to-one or onto either. But onto always seems kind of like a trick question. It's not meant to be, but most of the time it's yes. So are there questions on example A? Okay, so now we can probably look through the next three a little bit more quickly, we don't have to talk about all those definitions in length again. So if we look at B, now this is given as a table, still represents ordered pairs. We can more clearly see the x values labeled and the y values labeled. So if we list our domain, the x's, notice +2 repeats and -1 repeats. So I just need to write down those two values once. So I'm going to write them in order. We have -2, -1, and +2 for the x values. The y values, as you look at them, are all different. And actually in the table, they're already in numerical order. So I can write those 5 values down, -2, -1, 0, 1, and 2. So looking at how we discussed what to look for in terms of a relation being a function, would you say this is a function? I see some no's. I agree. Why is it not? John? Yes. The x value 2 is paired with more than one y value, so is the x value -1. So it's not a function. That means you don't look to see is it one-to-one or onto. You only look for these if it is a function. So if it's not a function, you just find domain range, say it's not a function, and you're done. Questions on that one? Okay. Excuse me. Example C. So this is given as a graph, but you can see the points that are graphed there. Some of you might be able to answer these questions just looking at the graph the way it is. Some of you might want to label what these ordered pairs are before you answer the questions. So I'm going to label them in case that is helpful to anybody. So I'm going to try to go from left of the graph, move over to the right. So the leftmost point, would be if I go left 3 up 2, so that's negative 3, 2. I'm going to label them right on the graph if you labeled them off to the side. It's up to you. Some of you might not need to label them. And then kind of moving to the right here, so I have left 2 up 1, so negative 2, 1. But I also have left 2 down 2, which would be negative 2, negative 2. And then I have left 1 up 1, so negative 1, 1. And then on the y-axis, that's just up 2, so that would be 0, 2. And then moving to the right, right 1, down 2, so 1, negative 2. Next one would be right 3 and down 3, so 3, negative 3. And then right 4 up 4, so 4, 4 would be the top rightmost point. So now by labeling the points, I can more clearly see the x and the y values to list my domain and range. So domain, if I'm listing in order, so x values I would be looking left to right. So I have an x value of negative 3, an x value of negative 2. I only have to write that once. X value of negative 1, 0, 1, 3, and 4. And then for the y values, for the range, so now I can look bottom to top if I want them in order. So my lowest y value is negative 3, and then I have a y value of negative 2. I only need to write it once. A y value of 1, 2, and 4. Again, if they're repeated, you don't need to write them more than one time. And then would you say this is a function? I see some no's. So 2 of the ordered pairs have that same x value of negative 2, so no, it's not a function, meaning it's not one-to-one or onto either. Okay, and then the last one, so this is given as a mapping. Mappings are nice because it literally tells you what the domain and the range are, so you just have to write those values as a list. So domain, we have negative 3, negative 2, negative 1, 0, and 1. And then range, we have 0, 2, 4, 6, and 8. And how a mapping works, in case you're not as familiar with mappings, so this is saying the x value negative 3 is paired with the y value 0, so as an ordered pair, that would be negative 3, 0. For how to read that, so negative 2 is paired with positive 2, and so on. So is this a function? Heard some yeses, see some shaking their head, yes. So yes, it is a function. Every domain value is only paired with one y value. We don't have 2 arrows stemming off of the same x value. So then is it one-to-one? Jen? Yes? I saw some no's though. Reasons why it's yes or no, Hunter? If it has a repeated y value, it's not one-to-one. That's, well, so is there a repeated y value? Yes, 6. So negative 1 is paired with 6 and 1 is paired with 6. So if there's a repeated y value, it's not one-to-one. So it's a function, not one-to-one. Is it onto? I saw no right away. Why not? Yep, 8 is just left over. So really, this is the only case. It's not a trick question. This is the only case where you would say no is if you have a mapping and you see there's a value not being used in the range. You're only saying that because I said it seems like a trick question. You're right. I never did say that. But it doesn't have to be either of them. Now you know. So now you know. Yes. Now you know. So yes, it can be a function. It doesn't have to be one-to-one or onto. It can be both. It can be neither. It can be one or the other. All right, so then the remaining on this page, still under analyzing relations and functions, first we have the difference between what would be a discrete relation versus a continuous relation. So a discrete relation is a relation in which the domain is a set of individual points. So the graph would consist of points that are not connected. And then a continuous relation is a relation in which the domain has an infinite number of elements and can be graphed with a line or a smooth curve. And it does give an example if you needed to see that visually, separate points or a line, smooth curve. How this is used most of the time is, say you had a specific scenario and you knew that X represented, say, number of hours worked, and then Y represented the amount of money you're making, your salary, things like that, your hourly wage. When you know that the X's and Y's represent specific quantities and you're graphing the points and you have to decide whether or not to connect the points, that's really where this comes into play. So it's not just me giving you a graph and saying, is this discrete, is this continuous, when it's already graphed for you. It's you determining when you graph something whether or not it makes sense to connect the points is where that's really used. And then the last thing on this page, the vertical line test. We'll actually talk about this in the next example, but you may remember this from Algebra 1. I'm not sure if it was used in geometry. But if you have the graph of a relation, the vertical line test tells you whether or not it's a function. So here we have the graph of a parabola. If I were to draw a vertical line through it, or some of you might be familiar with maybe holding up your pencil or your pen to it, if any vertical line, anywhere I place it, only crosses or intersects the curve one time, then yes, it's a function. But if I draw a vertical line and it intersects 2 or more times, then it's not a function. So that's what the vertical line test says. So actually, if you look back up at example C, we already said it's not a function, and because we have a graph, I can show you by the vertical line test why it's not a function. If I drew a vertical line through the x value -2, notice you're traveling through 2 different points. So by the vertical line test, it's also not a function. And the reason why is when you pass through more than one point, that means more than one point has the same x value, so it's kind of tying those two ideas together. So in the next example, the second part now is focusing on using equations to represent relations and functions. And it's a little more challenging, I guess, to just look at an equation and say, yes, it's a function, no, it's not. So what this is explaining up here is that to determine whether an equation represents a function, it's often simplest to look at the graph of the relation. And once you have the graph, you can use the vertical line test. So the previous examples were sets of ordered pairs, tables, graphs already made for you, and then a mapping. So here the last way to represent them is an equation. And to determine if these are functions, we typically would graph them first and then use the vertical line test. So in example 2, it is asking us to identify a lot of things, but our first step is to graph the equation y equals x squared plus 1. So what I want you to think about is, how would you graph this? So kind of go way back to when you first learned how to graph something, before you learned any shortcut ways to graph an equation. I'm looking for a method of graphing that always works. That's probably the first way you ever learned how to graph something. You can kind of read my mind. Or even think about this, how would you graph y equals x squared plus 1? Say it louder. No, a table. All right, this is probably the first way you ever learned to graph a line. Before you learned slope-intercept form, you probably graphed lines using a table. So tables always work. No matter what your equation is, if you forget a shortcut way for how to graph something, make a table. It always works. In the table, you can choose whatever x values you'd like. Typically, you should probably choose them so they actually fit on your graph, so our x value should be in between -10 and 10. I kind of default to these x values. So I like to use 0, some negative numbers, some positive numbers, but really you could use different ones. It would still be okay. And then I just need to substitute those x values into the equation and then evaluate to find the y value. So if x is -2, I replace that with x. So I have -2 squared is +4, and then +1 is 5. So that y value is 5. And then for -1, -1 squared is 1, +1 is 2. If x is 0, 0 squared is 0, +1 is 1. If x is 1, 1 squared is 1, +1 is 2. And then if x is 2, 2 squared is 4, +1 is 5. And that at least gives me now 5 points I can plot on my graph and then connect them to draw in either a line or a curve if it isn't a line. So -2, 5, left 2 up 5. This is the first time we're plotting ordered pairs, so just make sure that you're plotting them correctly. -1, 2 would be left 1 and then up 2. 0, 1 is just up 1 on the y-axis. 1, 2 is right 1, up 2. 2, 5 is right 2, up 5. And then I should connect these points, not only connect them, but draw my curve through the last points I have on there, draw arrows to show it's continuing. Because I really could have plugged in any x value, I just chose to plug in those 5 x values. And there's the graph. All right, so then once you have a graph, it says determine the domain and range. Now, the way we're going to write this domain and range is different from how we wrote it in the previous examples because, like I said, I have x values listed here, but I know these are not the only x values in the domain. I could have chosen -19 if I wanted to. It wouldn't fit on my graph, so it wouldn't make sense, but I could plug in -19 and get a y value. I could also plug in 20.5 if I wanted to. I would get a y value. Again, it wouldn't fit on my graph, but I could plug it in. So the point I'm trying to make is x could really be any number I want it to be. So x is really from the set all real numbers. And I have that notation up here. You can ignore this underneath it. But all real numbers, so that capital R, but it has the double line. If you just wrote this for the domain, that's okay. I'm going to show you on here how to write it in the set builder notation. And I want to make this clear. I'm showing you this because if you take a math class beyond Algebra 2, you're going to see this notation that I'm going to write down. In this class, say on your quiz, you just write this, it's okay. You don't have to write this whole thing out. So in set builder notation, this is how it would be written. The domain is the x values such that, so it starts out like we used it last chapter, define your variable, such that. And then we want to say x is an element of this. The element symbol, it looks like a C within a line, so it isn't E, but that means element of. And then the all real numbers symbol. So the domain is all x values such that x is an element of the set of all real numbers. Would be the more formal way to write it. X could be anything. Looking at the graph for the range then, would you say that y could be any number? I see some no's. There is a restriction on y because with the graph the way it is, it's a parabola. Notice the vertex, the lowest value y can be is 1. Any value less than that, the graph doesn't exist. So all your y values have to be 1 or higher. So in set builder notation, it would be the range is the set of all y values such that y has to be greater than or equal to 1. If you just had the inequality, again, that's okay for this part. That's the set builder notation. And this probably looks more familiar anyway. That's how you were writing, or should have written, solution sets on your quiz. So that's domain and range in this type of example. It then also asks us, and keep in mind on a quiz, I'd have this laid out differently so you made sure you were answering every question. It says now to determine whether the equation is a function. So in looking at the graph, using the vertical line test, is this a function? Yes. This one's a little bit easier because I know when we talked about the vertical line test, it was already a parabola. So yes, it's a function. Any vertical line would only pass through our graph at one point, anywhere I drew it. So then since it's a function, we can then decide, is it one-to-one, is it onto? So would you say it's one-to-one? I heard some no's. One-to-one means no repeated x or no repeated y values. You can even look at your table and see the y values are repeating. So no, it is not onto. So I'm just going to put not, or one-to-one. I'm sorry, I'm getting these mixed up. I don't mean to be mixing you up. It's not one-to-one. And then onto, would you say it's onto? Yes. So yes, it is onto. You don't then have to say both or neither if you've already said it's not one-to-one, but it is onto. You've already answered the question. And then looking at how we graph this, is it discrete or continuous? All right, it made sense when we were graphing it to actually connect our points, so it is continuous. I even had said to make sure you draw your arrows at the end to show it is continuing, so that could have kind of led you to believe it's continuous. So make sure looking at your directions when you get to your practice, you do have a worksheet that you're answering all those questions. On a quiz, like I said, I would have it more laid out so that you're making sure you're answering every question and you don't lose points just because you missed something. What this part says here before we get into function notation, which is the last thing, if you hear the terminology independent variable and dependent variable, that's just saying here that an independent variable, this is the variable that makes up the domain, so it's typically your x values. If you're using the variables x and y, it's typically your x values. And then the other variable is called the dependent variable, and this is often the y value, since y in an equation often depends on x. So a way to explain that is when we made our table, we plugged x values in to find the y value, so y depended on what x was, is a way to think of that. So typically, if your variables are x and y, x is independent, y is dependent. But if that terminology comes up later, we'll continue to talk about that. So the last thing is that when equations do represent functions, they're often written as a function in function notation, which this was also part of Algebra 1. So what I have here is an equation, and here is that same equation written in function notation. So the only difference is rather than having y equals, you have this notation with the f and the x. and this is red, the way you say this is f of x. It does not mean f times x. It is not multiplication of f and x. It's read at f of x. So what's important for you to see here, that's the only difference between the form of an equation and then how it is written as a function. F of x means the same thing as y. If you see f of x, you could replace it with the variable y, and it means the same thing. So it represents a y value. So looking at example 3, we are given the function f of x equals 2x squared minus 8, and it says find each value. We're finding f of 6, and then f of 2y. So to find f of 6, notice looking at the f of x notation, the 6 is in place of the x, meaning 6 is the x value. So this is telling you that in your function, you should replace the x with 6 and then evaluate. So this would equal 2 times, replacing x, I would have 6 squared, and then minus 8. And then you evaluate that right side using order of operations. You don't do anything to the left side. The f of 6 just stays there. That's just telling you what to do. So evaluating this, I have to do the exponent first. So 6 squared is 36. So 2 times 36 minus 8. Then I have to multiply before I subtract. So 72 minus 8, and that is 64. So 64 is your answer. If you just circle 64, that's fine. If you bring down and you say f of 6 equals 64 and you have that whole thing as your answer, that's fine. I don't want to see you divide both sides by 6 though, because again, this is not f times 6. You're not solving for f. 64 is the answer. What this means, this is saying for this function, when the x value is 6, the y value is 64. So again, this isn't anything you have to write down, but I just want you to see what it means. This is really representing this ordered pair. So not only how to find a function value, but what it actually represents. All right, and then for B, we're going to work through this the same way, but we're finding f of 2y. So that means anywhere I see an x, I'm going to replace it with 2y. Now, because I have a variable in here, that means that variable is also going to be in my answer. My answer is going to be an expression and not just a value. So this will be 2 times, and then the quantity 2y squared minus 8. And now this one, I can't evaluate it because I don't know what y is, but I can simplify it. So I still need to simplify this exponent first. 2y, I had this up here before I erased it. 2y quantity squared means 2y times 2y. So what would that be? 2y times 2y. 2 times 2 is 4. Y times y, Claudia, is y squared. So 2y quantity squared is really 4y squared. Then I still have the minus 8. And then I can multiply the 2 with the 4 in the 4y squared. So that would be 8y squared. I still have the minus 8. And now these are not like terms, so I can't subtract the 8s and get 0 somehow. This is the answer. That's in simplest form. I don't have any parentheses. I don't have any like terms. That's it. Okay, questions? Okay, I'm going to pass out your assignment. While I'm doing that, go ahead and answer A and B in example 4. And notice function notation doesn't have to use the variable f. So this gives you the function g of x is x cubed minus 3, and it says find g of negative 2 and g of 2f. So go ahead and work on those. I'll pass out your assignments. If you have these two done as I'm walking around, I can check them. Otherwise, I'll show the answers when I get back up here for you to check. And then you have the remaining 2 minutes to work, or like I said, if you want to see your test today, I don't have time to pass them back, but you can come up and see it. Did everybody get one? All right, so I will show what those answers to A and B should be for you to check. Let me know if you have questions. And like I said, there's about 5 minutes left. So not a ton of time, but you can get started on the worksheet. If you want to see your test today before I pass it back tomorrow, you can come up and I can get your test out. Did you see your grade? Did you see your grade?
I did. You know how disappointed I was when I found out I didn't get my sticker?
I just need your test back, obviously, but
So how would you get the first notation, right? That completes the 5 lines.
interval notation, so that's with the parentheses and the brackets.
Yikes.
I don't
And
know.
the infinities. So
Oh,
like if this was graphed, it'd be a dot at 6 shaded down. So it'd be negative infinity up to 6. So it would look like, I don't have the, yeah, you can just find it so you can see it. So it would look like this.
oh, okay.
And then this would be the one for 26. There'd be 2 intervals.
Okay.
I had 6 tests. I did 99.5%. Like, each guy was 6. I had a streak of 4 straight, half off. So, yeah, that was one. Oh, half points for you really do. And you were a point away, thank you. I didn't know.
Well, Grace said growing up, and I didn't know. And then I got an owl, put mine next to Grace's face from the sun too.
Did you get to see your final? Like, do you know what you got your point on?
She said she has it, but
It's 1 point off.
probably honestly something that me not thinking through it, like 4 plus 2 is 5.
Yeah, something little. Yep. Did she put extra credit on her final?
I don't think so.
Okay, I don't either.
Our excellence were for a horse.
I'll say it has to go through the x value 7. So does that pass?